Hello students, this lecture is in continuation to the previous lecture, that is Green's theorem. Here we are going to discuss some of the applications of Green's theorems. So first application, we are going to discuss area using Green's theorem. So we know that Green's theorem, if C is any simple smooth or piecewise smooth closed curve bounding the region R, then the integral of the circulation f dx plus g dy is equal to the surface integral, area integral, curly g by curly x minus curly f by curly y dx dy. So here if we will take f is equal to 0 and g is equal to x, so what we will get, x 0 dx x dy, which is x dy, f0 gx, it is 1 minus 0 dx dy. Derivative of x with respect to x is 1 and derivative 0 with respect to y is 0. We get dx dy, and we know that in the previous semester we have discussed that it is representing what, the area bounded by the region R. So area of the region R can be calculated by using the formula x dy along the curve C. That curve C is bounding the area R. Now if we take f is equal to minus y and g is equal to 0, we'll get this. So here area become what, minus y dx, and if we'll take f is equal to minus y and g is equal to x, we'll get this after simplification. So area become what, 1 by 2 x dy minus y dx. So we can use any of these three formulas to calculate the area bounded by the closed curve C. So here it is C, it is not R, mistakenly I have written this R, but you can replace this by C. Everywhere it is C. So whenever you are asked to calculate the area bounded by the curve C, you can use, it is x dy minus y dx, or you can use x dy circulation minus y dy circulation 1 by 2 x dy minus y dx. Now let us apply that formula to calculate the area bounded by these curves. Take x is equal to a cos theta and y is equal to b sin theta. 0 to theta varies from 0 to y. So to use that formula, we want the value of x and the value of dy. X we already have given, and dy we have to calculate from this. Dy is the derivative of this. It is derivative sign is cos, so it is with d theta, dy by d theta is b cos theta. So value of dy become what, b cos theta d theta. So substitute the values. X is a cos theta and y is b sin theta d theta. Multiply, divide by 2, it is cos square theta, 2 into cos square theta, 2, we multiply and divide by 2. Replace this to cos square theta by 1 minus cos theta. Integration of 1 is theta, and cos 2 theta integration is sin 2 theta by 2. Substitute the limit, 2 pi minus 0, sin 4 pi is 0 and sin 0 is 0, so we got pi ab. If you observe, it is a parametric equation of the ellipse. So we know that the area of the ellipse is pi ab, so the formula is working fine. Next, take x is equal to a cos theta and y is equal to a sin theta, and theta varies from 0 to 2 pi, and you are asked to calculate the area bounded by this curve. If you observe carefully, it is nothing but the parametric equation of circle. So area should be what, pi a square. So using the formula x is equal to a cos theta and dy is equal to a cos theta d theta, we got what, pi a square. So it is the formula for area of circle. So that again it is working fine for this example also. That means we can use this formula to calculate the area bounded by any closed curve C. You can use any of those three formulas, out of which I am using this one. Why? Because this one is the simplest one. In second one there is minus, there may be a difficulty in handling minus sign in the calculations, and in a third one there is the difference of two integrals, so better is to use this formula to calculate the area bounded by the curve. Next is use Green's theorem to prove this identity. Curly u by curly and ds is equal to del square u by dx dy, where curly u by curly and the directional derivative of u in the direction of n, del square u is the Laplacian operator, and this n is the unit normal vector to the curve C, unit normal outer vector to the C. Now to calculate the unit normal vector, let us consider the parametric form of the curve. So parametric form of the curve is represented by r vector is equal to xi plus yj. It can be in terms of t or it can be in terms of s. So here we are using s, the arc length parameter. Why? Because we have arc length in the integral, so it is ds. Now to calculate normal, first of all we are going to calculate tangent. We know that derivative always point in the direction of tangent, so dr by ds is dx by dti dy by dtj. It gives us what the tangent, and to calculate the normal vector we have to use this relation. We have to choose such a n which will give us a dot product with the t0. Why? Because the tangent and normals are perpendicular to each other. So I took this here and this here with minus sign. When we multiply, when we take dot product, we'll get 0. So this is our normal n cap. Now curly u by curly n is directional derivative u in the direction of n. How to calculate the directional derivative? Gradient into the unit vector in that direction. Del u formula is curly u by curly x I, curly u by curly y j, and n cap is dy by dsi minus dx by dsj. So multiply these two, will get this. Substitute into the formula which we are to prove. This ds get cancelled, we will get this. Now apply the Green's theorem here. Consider this as f and this as g. Apply this formula, we will get this. This is nothing but the Laplacian operator. Hence the result is proved. So you can say that is another form of Green's theorem. Curly u by curly and ds is equal to del square u dx dy. Now use this formula, find the value of curly u by curly and ds for this u and for this curve. Now we know that curly u by curly and ds is equal to del square u dx dy. So it is always better to see, you can calculate both ways, but it is always easy to solve the integrals in higher dimensions. Why? Because we have scopes to move in two directions. We have 2 degrees of freedom. In one dimension, in line integral we have only 1 degree of freedom, but in area integral we have 2 degrees of freedom, so it is better to solve it in area dimension. So this is u, you have to calculate del square u. U is x square plus y square. Calculate the second partial derivative with respect to x and second partial derivative with respect to y. It is 2, substitute there, 2 plus 2 become what? 4. Substitute this value 4 here, we get what? 4 dx dy. And we know that dx dy represents what? The area bounded by the given curve C. So what is area bounded by the region R? This is our region R, so its area is 1/4 of the total area of the circle. So I can use that 1/4 of the total area of the circle. The circle is with radius 3. Why? Because it is 9. So it is 3 square, so radius is 3. 4 becomes the answer is 9 pi. So this integral become what? The 9 pi. This is the final answer. Similarly, we can apply this for this u and this curve. Calculated here second order derivatives, substitute into the formula, we get 4x substitute this 4s here This become x dx dy. We missed this 4, but we have to write this 4 here, write 4 here, write 4 here, and write 4 here. It should be 48. You should be careful words, you have to write 4 4. Next is, you have given a double integral and you're asked to convert it into signal line integral, then solve. How to convert double integral into line integral? By using the Green's theorem. So we have given double integral, so we have to compare this with this. So here curly g by curly x become what? Y square, and curly f by curly y become what? 0. If we compare this with this, y square dx dy, we get curly g by curly x y square, and curly f by curly y is 0. Y square can be written as y square minus 0, no issues at all. So this value is now y square, and this value is now 0. So in order to get the value of g, we can integrate this with respect to x. So it will become y square x, and this is 0. Here actually we are not integrating, we are searching for such a function which will satisfy these two equations. So its partial derivative with respect to x is y square, and it is 0. So there are so many other functions, but we have to consider the simplest one. Now this become what? This is value of g, this is value of f. It becomes x square y dy. The given curve is ellipse. The standard form of the ellipse is this parametric form we know that 4 cos theta and 2 sin theta. So whenever we have to solve the line integral, your first aim is to convert everything in terms of single variable. So here, unless you are not ready with a single variable inside, you cannot integrate. First of all, you have to convert everything in terms of one variable. So we use the parametric form, we converted everything in terms of theta, and thereafter integrated, we get the final answer. Here we apply symbolic 0. 2 minus 1 is 1, 2 minus 1 is 1, and 2 plus 2 4, 4 minus 2 is 2. Both are even, 5 by 2. Similarly, you can apply the same on the next. Here curly g by curly x is y, and curly f by curly y x. So integrate x, integrate y. So it is the simplest possible functions for which its partial derivative with respect to y is this, its partial derivative with respect to x is this. Substitute, so you will get the 0 answer. Thank you very much. In next lecture we'll start the surface integral.